All right, let's dive right in. Have you ever stopped to think about how your phone, your computer, heck, even your thermostat actually thinks? Well, it all boils down to this fundamental language, a language spoken in tiny pulses of electricity. And today, we're going to decode that language by exploring the two main dialects that pretty much run our entire world, analog and digital signals. So, here's the roadmap for today. We're going to start with the big picture, analog versus digital. Then, we'll break down what a signal actually looks like. After that, we'll get hands-on with our main tool, the oscilloscope, learn how to read it and even measure a signal. And finally, we'll wrap up by talking about why all of this is so important. Sound good? Let's jump in. All right, first up, the analog versus the digital world. You can almost think of it as a clash of philosophies, right? On one side, you have continuous, super precise detail, and on the other, you've got this beautiful, discrete simplicity. Let's make this super simple. Think about a thermostat. You know, one of those old school analog ones with a little dial. That thing could, in theory, point to exactly 72.482 degrees. It's totally continuous. There's an infinite number of points between 72 and 73. But your shiny new digital thermostat? It just says 72. It takes that messy, real-world number and snaps it to a clean, discrete value. And for a computer chip, that is so much easier to deal with. And that, in a nutshell, is an analog signal. It's a signal that can be any value within a certain range, just like that thermometer. It's a perfect mirror of the real world, because the real world is all about smooth, continuous changes. Now, that precision is awesome, but it can also be, well, kind of messy and complicated for a computer to work with directly. Now, on the flip side, you have the digital signal. This is where we simplify reality into a limited set of values. And usually, it's just two, on or off. Yep, that's it. It's less precise for sure, but that simplicity, that's its superpower. There's no gray area, no kinda on. It's either on or it's off, which makes it incredibly fast and reliable for electronics to understand. Okay, so we get the basic idea of analog versus digital, but what do these things actually look like? If we could somehow see the electricity, what would we see? Well, that's where we get into the anatomy of a signal, the language of waveforms. So analog signals can come in all kinds of flavors. You've got your classic smooth sine wave, you've got more complex repeating shapes, and then you have, wait a second, a square wave? Doesn't that look, digital? And that's a great question. But here's the catch. This one is still considered analog. And the key reason why is that its minimum value dips into negative voltage. True digital signals, as we're about to find out, play by a much stricter set of rules. Now, when you look at any kind of repeating wave like this, there are a couple of key things we need to know. First is the amplitude. That's just a fancy word for its height. How tall is the wave? We can measure it from the middle to the peak or from the very bottom to the very top. The second thing is its period. That's simply how long it takes for the wave to complete one full pattern before it starts repeating itself. Okay, remember how we said digital is simpler? Well, here's what we mean. It's way more black and white, or more accurately, high and low. A logic level is just a specific voltage that the computer agrees means something. So for the systems we're talking about, anything around 5 volts is considered high. That's a 1. Anything close to 0 volts is low. That's a 0. And that no man's land in between, that's an invalid state. Electronics are specifically designed to stay out of there. So a digital signal has its own special anatomy too. The amplitude is usually fixed. It's either 0 volts or a nice clean 5 volts. It also has a period, just like the analog wave. But now, we're also really interested in how long it stays high versus how long it stays low. And those super sharp vertical jumps, those are absolutely critical. The jump from low to high is the rising edge, and the drop from high to low is the falling edge. Those edges are often what trigger actions in a circuit. This is all great, but how in the world do we actually see any of this? These are invisible pulses of electricity, right? We need a special window, a tool that lets us peer into the secret life of circuits. And that tool, my friends, is the oscilloscope. An oscilloscope is just an incredible piece of equipment. At its core, its whole job is to draw a graph for you, but it does it unbelievably fast. The vertical axis, that's your y-axis, shows you voltage. The horizontal axis, your x-axis, shows you time. By plotting voltage against time, it literally lets us see electricity. We can see the exact shape and behavior of any signal we plug into it. Okay, let's take a look at the one we'll be using. I know. All those knobs and buttons can look pretty intimidating at first. But don't worry, we only need to care about a few key things. See this control here? That's the time base. Think of it as the zoom for the horizontal or time axis. This one over here is the channel scale. That's our zoom for the vertical or voltage axis. And see these little lines we can move around? Those are markers, and they're going to be a handy shortcut for us in a little bit. All right, this is probably the most important part of this whole thing. It's cool to see the wave, but how do we actually translate what's on this screen with this grid into real useful numbers? How do we actually read the thing? Believe it or not, it boils down to a dead simple 3-step process. Seriously. Step 1. Find the scale. The scope will tell you how much time or voltage each one of those grid squares represents. Step 2. Count the squares. Just count how many squares your signal covers. Step 3. Do the math. Multiply the number of squares by the scale. That's it. Find the scale, count the squares, do the math. That's all there is to it. So let's take voltage, for example. We're looking at the vertical axis, right? Up and down. If the scale says 1 volt per division, that's 1 volt per square, and your wave goes up, say, 3 squares high. Well, 3 squares times 1 volt per square is 3 volts. See? Simple. And you know what? It is the exact same logic for measuring time, just sideways. You look at the horizontal axis, find the time scale, maybe it's 1 millisecond per division. You count how many squares a full wave cycle takes up, you multiply, and boom, that number is your signal's period. Okay, enough talk. Theory time is officially over. We know what these signals are, we have our tool, and we have our simple 3-step method. So let's put it all together and actually measure a live signal. All right, here we go. We've got a nice digital signal on the screen. The scales are right there for you to see. Let's put our new skills to the test. Let's see what we can figure out about this thing. Okay, let's walk through this together. First, amplitude. That's the vertical part. The signal goes up 2.5 divisions, right? And the scale is 2 volts per division. So 2.5 times 2, that gives us an amplitude of 5 volts. Perfect. Now for the period, the horizontal part. 1 full cycle takes up exactly 4 divisions. The time scale is 2 milliseconds per division. So 4 times 2 gives us a period of 8 milliseconds. Easy. But we can figure out even more. Let's talk frequency. That just means how many times does this wave repeat every second? The formula is super simple, just 1 divided by the period. So 1 divided by our 8 milliseconds gives us 125 hertz. Next up, duty cycle. This is a really important one. It tells us what percentage of the time the signal is actually on. It was high for 4.8 milliseconds out of that total 8 millisecond period. Do the math, and that's a 60% duty cycle. This is the kind of thing you'd use to control the speed of a motor or dim an LED. Now, I'll be honest, counting all those little squares can get old fast. That's why most modern scopes have this awesome shortcut, markers. Remember those lines from earlier? You can just drag one to the beginning of the wave and the other to the end, and look at that. The scope does all the math for you and tells you the difference is exactly 8 milliseconds. No counting needed. Super handy. So we've gone deep on how to measure all this stuff. But you might be thinking, okay, this is a course about digital electronics, so why do we care so much about the analog world? And that's a fantastic question. It really comes down to this fundamental truth. Even though we're focused on digital, it's so important to remember that the world around you is analog, right? Sound, light, temperature, pressure, it's all smooth and continuous. Our digital gadgets, which only think in ones and zeros, have to constantly translate. They're always taking in that messy analog world, converting it to clean digital data, doing their magic, and then converting it back out so we can hear or see it. If you want to build that bridge between the two worlds, you absolutely have to understand both sides. Look, what this really all means is that by learning to read a tool like an oscilloscope, you've basically given yourself a superpower. You've learned how to see the invisible. This is the fundamental language that's being spoken inside every single piece of technology you own, and that's incredibly powerful. So the only question left is, now that you can see this invisible world, what are you going to decode next?